Okay, so here we begin with production functions. If I can get the screen up here. There we go. Okay, so I want to talk about production functions. These are models, really, that come from business and microeconomics, but they play a fundamental role in allowing us to model our systems. So I'm going to describe what they are for you and go through some examples and so forth. Okay. Talk about marginal analysis. That'll be clear what that means when I finish here. I'm not sure how long this is going to take, so this may be multiple videos. I'm not sure. So production functions are models that allow us to transform physical resources that we put into a system into its outputs. So I have an example here. So speed and temperature and humidity and so forth. These are inputs to maybe a driving experience, and the outputs would be the rate of emissions, tons per vehicle mile. Of course, another transportation example. Aircraft fuel pilots would be the input in an airline system, and the outputs would be number of passengers, cargo tons, emissions from the aircraft. Could be fuel consumption in gallons, that sort of thing. So the idea is that we're taking typically one output and relating it to inputs in a mathematical model. And why do we want to do this? Well, we want to, as always, we want to be able to model a system. We need to be able to model a system if we're to design it, analyze it, right, scope it out as we're doing in this class. Right? So it behooves us to understand how to, this class of models and how to develop them. And also, if we have a model of a system, we can explore possibilities with it. And that's what that flexibility idea was that we talked about in class, right? So being able to look at different options that we have and model them and predict what will happen if we change something. And as I said, all of these models derive from microeconomics. So. So this is very common structure that's used in modeling engineering systems. So chapter 2 in the new book and chapter 2 from the old book both relate to production functions. The old book is more analytical in nature. So there are two types in general, and this is two types of any models that we derive. The first class of models are deductive models, that is, empirical models. So we guess at a functional form, we collect some data, and we calibrate the model using some technique like regression to come up with a relationship among the variables. Another approach is a mechanistic approach, the inductive reasoning. So we try to derive a model from first principles. And I'll give you some examples of these in a minute. Okay, simple example. So let's say we want to develop a model estimating the deflection in a simply supported beam. Now I did this example last year, and one of the students in the class was a structural engineer, and he was horrified at the example, but it works. I'll look at the deductive approach first. So if we define variables that we know are involved in this process, this system, simple system of a simply supported beam with a load. So the variables that are involved are the span, the load, the moment of inertia of the beam, and its elasticity, the elasticity of the material. So a deductive approach would be to set up a bunch of set up a bunch of little models in the laboratory and measure these variables, including the deflection. And assuming a functional form among them, we can then come up with a model, a math model that describes deflection as a function of all of these other variables. Right? So we're going to collect some data from the laboratory or from the field even, right? And then calibrate the model according to this functional form. So with production functions, a very common model function is something that looks like this, right? This is called the Cobb-Douglas formulation. I don't even remember the history. Cobb-Douglas are a couple of guys. Doesn't matter for our purposes, but this is very commonly used in developing production functions. So D is the deflection, P, L, E, and I are those four variables, and then the coefficients are the A's. So if we use the data, first of all, we have to calibrate this model. If we linearize the model using the approach that I described in the regression slides, we can then do a linear regression and develop or establish these A's. Right? And there is a model that we, for a simply supported beam loaded in the middle, this is what we might find with some variation. And of course, as I said, that structural engineer was appalled at doing it this way. Of course, he's used to looking at taking the mechanistic approach, the inductive approach. And there are a variety of different methods that have been used to do that, to develop a model for deflection based on these things that we know. Okay, but what we'll be using is the deductive approach, right? Assuming a functional form, collecting some data, and developing the model. This is the standard in economics, relatively easy to use. If we're not careful with the modeling, we might get some poor accuracy, but it's pretty easy to use. This is the standard in engineering, but we really need the knowledge of the process details, and the kinds of things that we're talking about may not lend themselves to being understanding. So, for example, why do people make choices? Right? That's too complex. These complex issues that involve human behavior really are much too complex to be able to allow us to use inductive modeling. So the Cobb-Douglas formulation is the one that we'll use. It's a pretty standard one. This is in general the form. Right? Pi stands for the product, the multiple product of the x's. And the approach to calibrating this model is to collect a bunch of data on y's and x's, linearize this model, and then do a linear regression to obtain the A values. You can test the significance of the A values. You can do all of the statistics that you want on these things to see which ones play a role, which ones don't. And then so you'd end up with a linear model that looks like this. And then once you get the statistics, you can transform them back. So the advantages, they're economist models, so they're easy to formulate, no technical knowledge required. A lot of times, like I said, we don't really understand behavior of the players involved. Right? And these are very easy to use. We can do a lot of really great stuff with them. So I've got an example here, and we're going to go through some examples of manipulating this, what these numbers mean, and so forth. But let's assume that I had some data on these resources, whatever they may be. These could be, say, for example, labor and capital investments. And this output could be the outputs in tons of a process. Right? I mean, that's a pretty typical production function. The textbook, by the way, the ASA textbook, gives some good examples of production functions as well. So if we plotted the function, it would look like this, where y is the vertical axis and m and n are the planar axes. So this is this can be calibrated and manipulated using Excel. And I was just looking at the time, and we're getting up there in time. So I'm going to finish this slide, and then we'll move on to the next video. So we can use Excel if we define the cells as the variables. We can actually set something up like this. Once we've calibrated the model, right, we can set something up like this and then do some what-if analysis. So we're going to stop here and continue with the next video.